over 7 decades, radio telescopes have been scanning the cosmos, listening for messages from the universe. Most of what they hear is cosmic static, the background hum of stars and galaxies. But occasionally, something extraordinary cuts through the noise. A signal so unusual, so unexpected, that it demands explanation. Today, we're exploring 7 of the most baffling radio signals ever received from deep space. These aren't random bursts of static. These are signals that have challenged our understanding of the universe, sparked intense scientific debate, and in some cases, raised the tantalizing possibility that we might not be alone. What makes a radio signal truly mysterious? It could be its incredible power, releasing more energy in milliseconds than our sun produces in days. It could be its precision, a narrow frequency that nature rarely produces. It could be its source, coming from a location that makes no sense. Or it could be its uniqueness, appearing once and never again, leaving us with more questions than answers. From signals that seem to come from our nearest stellar neighbor to bursts that arrive from billions of light years away, these radio signals represent some of the greatest mysteries in modern astronomy. Some have been explained, others remain baffling, and a few continue to inspire scientists decades after their detection. Whether these signals represent new astrophysical phenomena, technological interference, or something we haven't even imagined yet, they remind us that the universe is far stranger and more complex than we ever expected. Let's begin with the most famous radio signal in history, one that captured the imagination of scientists and the public alike for nearly 5 decades. On August 15, 1977, the Big Ear radio telescope in Ohio State University detected a strong narrowband radio signal that appeared to come from the direction of the constellation Sagittarius. Astronomer Jerry Emmon discovered the anomaly a few days later while reviewing the recorded data, circling the signal's intensity reading of 6 EQ UJ5 and writing, "Wow," beside it, giving the signal its now famous name. The Big Ear telescope was part of an early search for extraterrestrial intelligence project. The signal lasted for the full 72 seconds that Big Ear was able to observe it, which was exactly how long any point in space would remain in the telescope's field of view. What made the WOW signal so extraordinary was its frequency and intensity. The signal was detected near 1420 MHz, in what scientists call the hydrogen line. This is significant because hydrogen is the most common element in the universe, and scientists have long theorized that any advanced civilization attempting to communicate might choose this frequency, knowing that other technological civilizations would likely be monitoring it. The signal's peak intensity was represented by the letter U, indicating it was 30 standard deviations above background noise. This is extraordinarily strong for a signal coming from deep space. The alphanumeric sequence that Emmon circled represents the signal's intensity variation over time. The sequence 6EQUJ5 showed the signal rapidly increasing to peak intensity and then decreasing, as Earth's rotation carried the telescope past the source. What made this particularly intriguing was the signal's narrowband nature. Natural astrophysical sources typically produce broadband emissions across many frequencies. A narrow signal like this suggested either a very specific natural process or potentially an artificial origin. In the years following the detection, numerous attempts were made to detect the signal again. Despite numerous follow-up searches, the signal has never recurred. Over the decades, scientists proposed various explanations, but each was investigated and found wanting. In recent years, new theories have emerged. In 2020 observations made at the Arecibo, Observatory detected weaker signals with similar characteristics, leading to the hypothesis that cold hydrogen clouds in space, when bombarded by intense radiation from events like magnetar flares, could briefly emit powerful narrowband signals. While this explanation has promise, lead researcher Abel Mendez stated that the new findings don't solve the mystery of the WOW signal, but they give us the clearest picture yet of what it might be. Nearly 50 years later, it continues to fascinate us. A moment when something in the cosmos spoke in a language we could understand, even if we still don't know what it was saying. Fast radio bursts are bright, unresolved, broadband, millisecond flashes found in parts of the sky, appearing as single spikes of energy. Astronomers estimate the average FRB releases as much energy in a millisecond as the sun puts out in 3 days. The first FRB, known as the Lorimer burst, was discovered by Duncan Lorimer in 2007 while he was looking through archival pulsar survey data from 2001. When Lorimer announced his discovery, the astronomical community was skeptical. A signal that powerful, lasting only milliseconds, from outside our galaxy? It seemed almost impossible. But as more FRBs were discovered, the reality became undeniable. What makes FRBs so baffling is their sheer power combined with their brevity. These signals arrive from billions of light years away, yet they're bright enough to be detected across that vast distance. The amount of energy released is staggering. Because FRBs come from all over the sky and are not concentrated on the plane of the Milky Way, it indicates they have extragalactic origins. Most FRBs appear only once, flashing briefly and never repeating. This made them incredibly difficult to study. Then came a breakthrough. In 2012, the first repeating source, FRB 121102, was discovered. This was revolutionary because it allowed astronomers to track down its location with precision. FRB 121102 was identified with a dwarf galaxy 3 billion light-years away, in a region with incredibly strong magnetic fields. In 2019, another remarkable discovery was made. FRB 180916. The first FRB found to repeat on a regular 16.35-day schedule. This predictability was unexpected and opened new avenues for investigation. The first FRB detected within our own Milky Way galaxy occurred in April 2020. In April and May of 2019, the Breakthrough Listen project pointed Australia's Parkes radio telescope toward Proxima Centauri, the closest star to our solar system. This star, just over 4 light-years away, hosts at least 2 exoplanets, including the potentially habitable world Proxima b. While analyzing the data from these observations, researchers found something extraordinary: a narrowband signal at 982.002 MHz. This signal only appeared when the telescope was aimed at Proxima Centauri and vanished when it looked away. Precisely the behavior expected from a signal originating from that star system. Designated BLC-1 for Breakthrough Listen Candidate 1, the signal persisted for over 2 hours across 5 separate 30-minute observation windows. This made it the most promising technosignature candidate detected by the project since its start in 2015. What made BLC-1 so compelling was its frequency drift. The signal's frequency shifted over time, consistent with the Doppler effect from a moving source. Curiously, this drift was in the opposite direction of what Earth's rotation would cause, hinting that the source itself was in motion, perhaps on an orbiting planet. The signal was narrowband, occupying a very specific frequency, unlike the broadband emissions from natural astrophysical sources. This specificity, at a frequency with no known natural emission line, suggested either a very unusual natural event or an artificial origin. The discovery was made in the summer of 2020 by Shane Smith, an undergraduate intern who spotted the unusual signal while reviewing archive data. This highlighted how easily significant signals can hide within the massive datasets generated by these projects. When news of BLC-1 leaked to the media in December 2020, public excitement exploded. The possibility of a signal from our nearest stellar neighbor, a system with a potentially habitable world, captured imaginations globally. However, the scientific team urged caution. They emphasized that while the signal was interesting, extensive analysis was required before drawing any conclusions, as most promising signals end up having mundane explanations. Lead researcher Sophia Sheik headed the detailed analysis, subjecting BLC-1 to intense scrutiny. The team searched for all possible sources of terrestrial interference, checking satellites, aircraft, and local electronics. A primary challenge was to confirm whether the signal was truly from space or just a coincidence of Earth-based interference appearing when the telescope pointed toward Proxima Centauri. As the analysis deepened, problems emerged. The team found dozens of similar signals at other frequencies, all mathematically related to common clock oscillators found in electronic devices. Most tellingly, these similar signals also appeared when the telescope was not pointed at Proxima Centauri, suggesting the source was local and related to the observing process itself. The drift rate also raised red flags. A signal from an orbiting planet should show a cyclical drift rate, but BLC-1's drift was strangely linear, more like a malfunctioning electronic device. After months of work, the team concluded that BLC-1 was not an alien technosignature, but a complex form of local radio interference. The team's transparent publication of their findings in Nature Astronomy in October 2021 showcased the rigorous scientific process essential for SETI research. Beginning in 2001, the very same Parkes radio telescope began detecting brief, intense radio bursts that seemed to come from deep space. These mysterious signals were named peritons, and they were puzzling. They were millisecond-long transients that mimicked the dispersion pattern of a signal that had traveled through interstellar space, sweeping down in frequency just as a real cosmic signal would. This made them look alarmingly similar to fast radio bursts, or FRBs, which were believed to be genuine extragalactic phenomena. From the start, however, there were clues that peritons were terrestrial. They appeared equally bright in all 13 of the telescope's observation beams, indicating a nearby source was flooding the entire instrument. Yet, identifying that source proved difficult. Researchers investigated everything from lightning to aircraft to malfunctioning equipment, but no theory fit. The breakthrough came in 2014 when the observatory installed a new radio frequency interference monitor. In January 2015, the telescope detected 3 peritons, and the new monitor simultaneously captured signals in the 2.3 to 2.5 GHz range, a band used by microwave ovens. When PhD student Emily Petroff and her team realized the correlation, they tested the 2 microwave ovens on site. At first, simply running the ovens produced nothing. But then, they tried something different, opening the microwave door before the cooking cycle finished. Immediately, a periton appeared in the data. They had solved the mystery. When a microwave door is opened prematurely, the magnetron releases a burst of radio energy that perfectly mimics the dispersion of a cosmic signal. Further analysis of historical data revealed that peritons clustered around lunchtime, following human schedules, not cosmic ones. The solution was a relief, as it confirmed that FRBs were indeed distinct, real astronomical events. The Puritan story is a humorous tale about mistaking lunch for aliens, but it's really a story about the immense challenge of modern radio astronomy and the critical importance of eliminating false positives. FRB 121102 holds a special place in radio astronomy history as the first fast radio burst ever observed to repeat. Discovered in 2012, this source fundamentally changed how scientists think about these mysterious cosmic flashes. Before FRB 121102, all detected fast radio bursts appeared just once and then vanished. This made them nearly impossible to study in detail. By the time astronomers even realized they had detected something interesting, the source had gone silent, leaving only a single data point to analyze. FRB 121102 changed everything by producing multiple bursts over time, allowing for a much deeper investigation. The repeating nature of FRB 121102 allowed astronomers to determine its location with unprecedented precision. Using a network of telescopes, including the Very Large Array in New Mexico and the European VLBI network, scientists pinpointed the source to a dwarf galaxy approximately 3 billion light-years from Earth. This galaxy is remarkable. It's much smaller than our own Milky Way, yet it's incredibly active, churning out new stars at a furious pace. The environment where FRB 121102 originates appears to have extreme conditions, including exceptionally strong magnetic fields, thousands of times more powerful than those found in typical galactic neighborhoods. This extreme magnetic environment provided important clues about what might be producing the bursts. Scientists propose that FRB 121102 likely originates from a young, highly magnetized neutron star known as a magnetar, possibly located within a supernova remnant or near a massive black hole. The bursts from this source display fascinating characteristics. They arrive unpredictably, with quiet periods lasting weeks or even months, followed by periods of intense activity with multiple bursts per hour. The bursts also vary in brightness, duration, and frequency structure, suggesting a complex and dynamic emission mechanism. Between 2019 and 2020, Chinese astronomers using the massive FAST telescope detected an astonishing number of bursts from FRB 121102. Over a 47-day observation period, they recorded more than 1,650 individual bursts. This represented by far the largest set of FRBs ever recorded from a single source, more than all previously reported occurrences combined. This enormous dataset allowed scientists to analyze the statistical properties of the bursts in unprecedented detail, studying everything from their energy distribution to the timing between them. These bursts are so powerful, they can generate as much energy in 1,000th of a second as our sun does in an entire year. Analysis of this treasure trove of data revealed that despite the huge number of bursts, there's no simple pattern to their timing. They don't arrive in regular intervals or follow an obvious cycle. This unpredictability suggests the emission mechanism involves chaotic or turbulent processes rather than a simple periodic phenomenon like a pulsar spin. The discovery of FRB 121102's repeating nature also raised new questions. Are all FRB sources potential repeaters, and we just haven't observed the others long enough? Or are repeaters a distinct class of objects? Evidence now suggests both types exist, possibly representing different stages of the source's life or entirely different kinds of cosmic objects. FRB 121102 continues to be monitored by radio telescopes worldwide, and each new burst adds another piece to the puzzle. While we still don't fully understand what produces these incredibly energetic flashes, FRB 121102 has provided crucial insights that would have been impossible to obtain from one-time bursts alone. It was the key that unlocked a new era of RB research. In January 2025, astronomers announced a discovery that challenged the prevailing theories about fast radio bursts. They had traced an FRB to a galaxy that was for all practical purposes dead. This galaxy, roughly 2 billion light-years from Earth, is believed to be more than 11 billion years old, a relic from the early universe with no new stars being born. This discovery was significant because it flatly contradicted the emerging consensus about where FRBs originate. Most previously traced FRBs had been found in young, active galaxies bustling with star formation. The assumption was that FRBs were associated with young stellar populations, particularly young magnetars formed in recent supernova explosions. Magnetars are thought to be the most likely source of fast radio bursts. These are incredibly dense neutron stars with magnetic fields trillions of times stronger than Earth's. When these cosmic behemoths flare, they can release enormous amounts of energy. However, magnetars don't last forever. They are believed to be most active when they are young, gradually quieting down as they age over millions of years. Finding an FRB in an ancient quiescent galaxy raised some uncomfortable questions. If magnetars are the source, how could one still exist in a galaxy where star formation essentially ended billions of years ago? Young magnetars simply shouldn't be there. And old magnetars should have calmed down long ago, no longer capable of producing such powerful bursts. The discovery suggested several possibilities. Perhaps FRBs have multiple origins, with different types of cosmic events able to produce similar signals. Maybe some FRBs come from young magnetars in active galaxies, while others originate from entirely different phenomena in older systems. Another possibility involves binary star systems. The FRB might have originated from the merger of two ancient objects, like two neutron stars, or a neutron star and a white dwarf. Such mergers can occur in old stellar populations and might be capable of producing FRB-like signals through mechanisms totally different from young magnetars. Alternatively, this discovery might indicate that our understanding of magnetar evolution is incomplete. Perhaps, under certain conditions, old magnetars can experience late-life flares powerful enough to produce detectable FRBs, forcing us to reconsider the theoretical models of how these objects age. Dr. Tarane Eftekhari at Northwestern University, who led one of the studies on this FRB, noted that this discovery tells us that perhaps not all FRBs come from young stars, and that maybe there are multiple ways these signals are produced. The implication is that the FRB family might be far more diverse than we previously thought. The ability to trace this particular FRB to its host galaxy was made possible by the CHIME telescope and its outrigger stations, which can pinpoint burst locations with incredible precision. Understanding this diversity is crucial for unlocking the origins of FRBs. If different types of FRBs come from different sources, categorizing them correctly becomes essential. Properties like whether they repeat, their frequency characteristics, and their host galaxy type all provide vital clues. This discovery in a dead galaxy demonstrates that FRB research is still in its early stages. Despite detecting thousands of these bursts, we are still uncovering fundamental surprises about where they come from. Future observations will hopefully trace more FRBs to their hosts. A larger sample will reveal whether this old galaxy FRB is an oddity or represents a significant population we hadn't recognized. In 2022, astronomers studying a repeating fast radio burst, designated FRB 20,220,912, they discovered something never seen before. The signal's frequency was dropping over time, producing what scientists described as a cosmic slide whistle effect. The observation was made using the Allen Telescope Array, operated by the SETI Institute. Over 541 hours of observation, spanning approximately 2 months, researchers detected 35 bursts from this source. Each burst was carefully analyzed, revealing this fascinating and unexpected pattern. Most repeating FRBs show some variation in their center frequency from one burst to the next. This is expected and can result from changes in the emission mechanism. However, FRB 20220912 displayed something different: a systematic, progressive decrease in the center frequency of its bursts over the entire 2-month observation period. To help visualize this, scientists converted the frequency data into sound, mapping each burst's frequency to notes on a xylophone. The resulting audio sounds like someone playing a xylophone and repeatedly hitting progressively lower bars. The highest notes appear at the beginning, and the lowest notes appear at the end. This behavior is scientifically fascinating because it suggests something about the source itself is changing over time. The systematic frequency drift implies an evolving physical process, not just random variation. Dr. Sophia Sheikh of the SETI Institute, who led the study, noted that this work provided both confirmation of known FRB properties and the discovery of entirely new ones. The familiar aspect was a downward frequency drift within individual bursts, but the long-term trend across multiple bursts over months was completely novel. The observations also revealed other intriguing patterns. All 35 detected bursts were found in the lower part of the frequency spectrum being monitored, and each had its own unique energy signature. The team searched for patterns in the timing of the bursts, looking for any periodicity or mathematical relationship. Despite a thorough analysis, no clear pattern emerged. The bursts arrived unpredictably, highlighting one of the most mysterious aspects of repeating FRBs. If FRBs are produced by magnetars, the slide whistle effect might result from changes in the magnetar's magnetic field or rotation as it evolves. Alternatively, the effect might be caused by changing conditions in the material surrounding the source. The detailed observations made possible by the Allen Telescope Array's unique capabilities were crucial to this discovery. It can record a huge number of frequency channels simultaneously, allowing for instantaneous checks across the entire spectrum when an FRB arrives. The research team calculated that during the observation period, this one source was responsible for a few % of all strong FRBs detected across the entire sky. The cosmic slide whistle discovery reminds us that just when astronomers think they understand the basic patterns of FRBs, a source like this one comes along and exhibits entirely new behavior. As more repeating FRBs are monitored over long periods, scientists will learn if this effect is common or rare. Each new FRB discovery brings us closer to understanding these remarkable phenomena, revealing a complexity at every timescale that presents one of the greatest challenges and opportunities in modern astronomy. From the legendary WOW signal to the cosmic slide whistle of FRB 20220912, These radio signals represent some of the most baffling mysteries in modern astronomy. Each has challenged our understanding, sparked debate, and pushed the boundaries of what we thought possible. Some mysteries have been solved, teaching us valuable lessons about the rigorous process of science. Others remain tantalizingly unresolved. The WOW signal, nearly 50 years later, still lacks a definitive explanation. Fast radio bursts continue to surprise us with their diversity and power. What makes these signals truly special is what they represent: our ongoing quest to understand the universe. Every radio telescope scanning the sky, every researcher analyzing data, brings us closer to comprehending the cosmos. Perhaps somewhere in the data being collected tonight, a new signal awaits discovery. The search continues, the mysteries endure, and the universe, in its infinite complexity, keeps speaking to us in languages we're only beginning to understand. If you enjoyed this journey through the cosmos and want to explore more mysteries of the universe, please hit that subscribe button and give this video a like. Your support helps us continue bringing you fascinating content about space, science, and the unexplained. Don't forget to turn on notifications so you never miss our next cosmic adventure. Until next time, keep looking up, keep questioning, and keep wondering what signals might be reaching us from the depths of space.